Hello students, in today's lecture we will study about nomenclature of elements with atomic numbers greater than 100, electronic configuration of elements and the periodic table, electronic configurations and type of elements. This is the second lecture of Unit 3 wherein we had previously studied about modern periodic law and the present form of the periodic table. The importance of periodic table was already introduced in the previous class, and this is continuation of that. Let us start. Please note down the important points discussed in this lecture. The naming of new elements had been traditionally the privilege of the discoverer or the discoverers, and the suggested name was ratified by the IUPAC. In recent years, this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them are obtained. Their synthesis and characterization therefore require highly sophisticated, costly equipment laboratory. Such work is carried out with competitive spirits only in some laboratories of the world. Scientists, before collecting the reliable data on new element, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claim credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kurchatovium. To avoid such problems, IUPAC has made recommendations that until a new element's discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and numbers 1 to 9. These are shown in table 4. The roots are put together in order of digits which make up the atomic number, and m is added at the end. The IUPAC names for elements with Z, that is atomic number above 100, are shown in table number 5 in the next page. So table 4 shows the digit, name and abbreviation. For example, if the digit is 0, the name is nil and abbreviation is N. For digit 1, name is UN, and abbreviation is small letter U. For digit 2, name is BI and abbreviation is B. For digit 3, it is tri, that is small letter T. For digit 4, it is quad and abbreviation is letter small q. For digit 5, the name is pent and the abbreviation is small letter p. And for digit 6, name is sex and abbreviation is small letter h. For digit 7, it is sept and abbreviation is small s. For 8, it is oct So abbreviation is O. And for digit 9 it is N, ENN, and abbreviation is small letter E. Let us solve a a practical case problem to explain this concept further. Problem number 1. What would be the IUPAC name and symbol for the element with atomic number 120? What would be the IUPAC name and symbol for the element with atomic number 120? Solution. From table 4 shown on your screen, the roots for 1, 2 and 0, that is in the number 120 you have 1, 2 and 0 are, for 1 it is un, un, and for 2 it is by, and for 0 it is nil or n. So the abbreviation, hence the symbol and the name respectively are UBN. U for un1 represents 1, B represents 2 and N represents 0. And the name will be unbenilium. Table 5 shows the nomenclature of elements with atomic number above 100. Column 1 shows the atomic number, and column 2 name as per IUPAC, and column number 3 indicates the symbol, and column number 4 gives IUPAC, that is the official name, and column number 5 is IUPAC symbol. Please go through these numbers. Here in column number 1, the atomic number is given from 1012 up to 118. All the 18 numbers above 100 are shown here. The respective names, symbol, and IUPAC official name and IUPAC symbol are also displayed in the table number 5. Thus, the new element first gets a temporary name with symbol consisting of 3 letters, that is shown in third column. Later, permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or the state of that country in which the element was discovered, or it may pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by IUPAC. Electronic configurations of elements and the periodic table. In the preceding unit, we have learned that an electron in an atom is characterized by a set of 4 quantum numbers and principal quantum number n, which defines the main energy level known as shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals, s, p, d, f in an atom. The distribution of electrons into orbitals of an atom is called its electronic configuration. Please note that the distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. In this section, we will observe a direct connection between the electronic configuration of elements and the long form of periodic table. The periodic table and detailed discussions will be explained in the next slide. Meantime, we will just introduce electronic configurations in periods. The period indicates the value of n for the outermost or valence shell. In other words, successive periods in the periodic table is associated with filling of the next higher principal energy level, that is n equal to 1, n equal to 2, etc. It can be easily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. So please see the table here. In this table, there are 7 periods. First, second, third, fourth, fifth, sixth, and seventh. The orbitals, the respective in that particular period, are shown in column number 2 with number of electrons. So for example, consider the first period. In the first period, the number 1 is indicated before the shell number, and s orbital, there can be 1 to 2 electrons, and the corresponding elements are hydrogen and helium. Similarly, for the second period, 2s to the power of 1 to 2 number of electrons, and first orbital s, and in orbital p, 2p 0 to 6. There can be maximum of 6 electrons in the p orbital, and the corresponding elements are lithium and neon, so on and so forth. So all the 118 elements up to argon are shown here, as well as their respective periods. Detailed explanation we will continue in the next slide. We will continue our discussions on electronic configurations in periods by displaying the periodic table as shown on the screen. The first period, n is equal to 1, starts with filling of the lowest level 1s1. So hydrogen has 1s1, and therefore this period has two elements, hydrogen and helium. So this is the first period, 1s square. Helium has 1s square when first shell K is completed. The second period, n is equal to 2, starts with lithium. So n is equal to 2 is here. It starts with lithium. And the third electron enters the 2s orbital. The next element, beryllium, in the same period has 4 electrons and has the electronic configurations 1s square and 2s square. Beryllium has configurations 1s square and 2s square. Starting from the next element, boron. Boron is here at element number 5. The 2p orbitals are filled with electrons. So here 2p orbitals are filled up with electrons when the L shell is completed at neon. So L shell is completed at neon, that is 2s square and 2p to the power of 6. So this is a p block. Thus there are 8 elements in second period. The third period, n is equal to 3, begins at sodium and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. So the third period starts with sodium and ends with argon at number 18. The fourth period, n is equal to 4, starts at potassium and the added electrons fill up the 4s orbital. Now you may note that before 4p orbital is filled here, filling up of 3d orbitals becomes energetically favorable, and we come across the so-called 3d transition series of elements. So that is the element from at atomic number 21 to 30 are called the 3D transition series of elements. This starts from scandium Z is equal to 21, which has the electronic configuration 3D1 4s square. So this electronic configuration for scandium is 3d1 4s square. The third orbitals are filled, 3d orbitals are filled at zinc Z is equal to 30 with electronic configuration 3d to the power of 10 4s square. The fourth period ends at krypton Kr with filling up of 4p orbitals. Altogether, we have 18 elements in this fourth period. So, if you count from here to there, here that is from potassium to krypton, it will be 18 elements in the fourth period. The fifth period, that is n is equal to 5, beginning with rubidium, is similar to the fourth period and contains the 4D transition series starting at yttrium at Z is equal to 39. That is Z is equal to 39 is here. This period ends at xenon with filling up of 5p orbitals. That is Xc. Here it ends. The fifth period ends at Xc. The sixth period n is equal to 6 contains 32 elements. Please note it contains 32 elements and successive electrons enter 6s here 6s 4f 5d and 6p orbitals in the order. Filling up of 4f orbitals begins with ceridium at Z is equal to 58. That is at Z is equal to 58, 4F inner transition series, that is lanthanide series, starts. That is at 58 to 79 as a 71 we have inner transition elements called lanthanides, that is 4F 5D and 6s square. The seventh period n is equal to 7 here is similar to the sixth period with the successive filling up of 7s, 5f, 6d and 7p orbitals and includes most of the man-made radioactive elements. So here you see here after 89, 90 to 103 there is actinoids. This period will end at elements with atomic number 118. The seventh period will end at 118 OG, which would belong to the noble gas family. So this last vertical column is a noble gas column. Filling up of 5f orbitals after actinium, that is after actinium 89, gives 5F inner transition series known as actinoid series. The 4F and 5F inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Next, we will take up group-wise electronic configurations. Elements in the same vertical group have similar valence shell electronic configuration in the same number of electrons in the outer orbitals and similar properties. I will repeat, elements in the same vertical column or group have similar valence shell electronic configurations, the same number of electrons in the outer orbitals and similar properties. For example, group 1 elements, that is alkali metals. Group 1 elements, alkali metals, all have Ns to the power of 1 valence shell, that is 1 electron in the valence shell electronic configuration. Thus, it can be seen that the properties of an element have periodic dependence on its atomic number and not on relative atomic mass. Say for example, here you see 3 lithium. Lithium has three electrons, that is 1s square and 2s1. That is first shell 2 electrons and second shell 1 electron. Similarly, the case for sodium, potassium, rubidium, cesium and Fr. More discussion, the detailed discussions, we will discuss in the next slide with the help of the periodic table. The elements can be further classified into 4 blocks, namely S, P, S dash, P dash, D dash and F dash block, depending on the type of atomic orbitals that are filled with electrons. Electronic configurations and types of elements. The Aufbau built-up principle and the electronic configuration of atoms provide a theoretical foundation for the periodic classification. The elements in the vertical column of a periodic table constitute a group or family and exhibit same chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks, namely S block, P block, D block and F block, depending on the type of atomic orbitals that are being filled with electrons. This is shown in the figure on your screen. We notice 2 exceptions to this categorization. Strictly, helium belongs to S block, but its positioning in P block along with other 18 elements is justified because it has completely filled valence shell 1s square. This is the helium element and as a result exhibits the properties characteristics of other noble gases. Other exception is hydrogen, which is shown at the almost center of the screen. It has only one s electron and hence can be placed in group 1, that is alkali metal. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17, that is halogen family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure. We will briefly discuss about the salient features of the 4 types of elements marked in periodic table. More about these elements will be discussed later. S block elements. S block elements are those in which the last electron enters the outermost S subshell. They include elements of the first group and the second group. Their general outer electronic configuration is NS1 or NS square. So this is shown on the screen. You can see here the general outer electronic configuration is NS1 or NS square. See, for first period it is NS1 1S1 and 1S2, and for the second period is 2S1 and 2S2, so on and so forth. They are all reactive metals with low ionization enthalpies. They lose their outermost electrons readily from +1 and +2 ions to form. They lose their outermost electrons readily to form +1 and +2 ions. Their metallic character and reactivity increases down the group. They mainly form ionic compounds except lithium and beryllium. Next is p block elements. So previously we had studied S block. The general layout of the periodic table is shown on the screen. This was the S block which we discussed in the previous slide, and in this slide we will discuss about the P block which is in the right hand side. The P block in the whole of periodic table is shown here on the screen, the layout map, and its elements and details are shown on the right hand side of your screen. These elements are those in which the last electron enters the outer orbit, outermost p subshell. I will read once again. These are elements in which the last electron enters the outermost p subshell. They include elements of groups 13 to 18. So group 13 is this and group 18 is here. So these elements are in the groups 13 to 18. They are also called representative elements. Their general outer electronic configuration is Ns square Np to 1 to 6, that is Ns square, and in the S block, in the P block, they can be between 1 to 6 electrons. The 18th group elements are called noble gases. So this is 18th group number 18. All the elements in this column are called noble gases. They have completely filled orbitals. Their non-metallic character increases from left to right. So on the left hand side of the block are metals. On the right hand side are non-metals. So their non-metallic character increases from left to right in a period, and metallic character increases from top to bottom. So metallic character increases from top to bottom in a group. The D block elements. So D block lies between S block and P block. This is the layout map of the entire periodic table, and D block is here. From this block completely is D block. So D block elements, these are the elements in which the last electron enters in the penultimate D subshell. So it is not the last but one D shell, D subshell. They include elements of the group 3 to 12. So here you see here it is group 3 to 12. So D block is between group 3 to group 12 in the columns and 3D to 6D in the periods. They are also called transition elements. So D block elements are also called transition elements since they show a transition, that is change from most electropositive S block elements to least electropositive P block. So that is why they are called transition elements. Their general outer electronic configuration is n-1 d to the power 1 to 10 n s to the power 0 to 2. They are all metals, form colored compounds or ions, show variable oxidation states and valencies, paramagnetism and catalytic properties. I'll read once again. The group D elements are all metals, form colored compounds or ions, and they show variable oxidation states and valencies, paramagnetism and catalytic properties. F block elements. So there is a separate block. If you see look at the entire long form of periodic table, you have seen previously S block, P block, D block. The F block lies at the bottom. It is shown here separately as a table. These are elements in which last electrons enters the anti-penultimate F subshell. So these are the elements in which the last electron enters in the anti-penultimate subshell. They include lanthanides of 6th period. So lanthanide of the 6th period are from 58, atomic number 58 to 71. And 7th period, which starts from 90 to 103. Atomic number 90 to 103. And the names of these metals are also shown thereof in the above table. They are also called inner transition elements. So F is inner transition elements. It is also written in the table. Their general outer electronic configuration is n-2 into F to the power 1 to 14. So F can assume any value between 1 to 14 and n-1 into d to the power 0 to 1 ns square. They are all metals. So the elements in F block are all metals. Within each series, the properties of these elements are similar. Actinoids, that is the 7th period, are radioactive. So that is the last period. 7th period is all filled up with radioactive elements. Elements after uranium, that is uranium is at number 92, atomic number 92, and elements after uranium Z is equal to 92 in the actinoid series are called trans-uranium elements or trans-uranic elements or artificial elements. Metals, non-metals and metalloids. The elements can also be divided into metals and non-metals. Metals comprise more than 78% of all known elements and appear on the left side of periodic table. Metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium have very low melting points, 303 Kelvin and 302 Kelvin respectively. Metals usually have high melting and boiling points. They are good conductors of heat and electricity. They are malleable, that is, they can be flattened into thin sheets by hammering, and ductile, that means they can be drawn into wires. In contrast, nonmetals are located at the top right hand side of the periodic table. In fact, in a horizontal row, the property of elements can change from metallic on the left to the non-metallic on the right. right. See, these are all metals on the left side, and right side is non-metallic. So, non-metals are located at the top right hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic. In any horizontal row, left side is metallic and right side is non-metallic. The non-metals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity, and most non-metallic solids are brittle and are neither malleable nor ductile. So, non-metals are poor conductors of heat and electricity, and they are brittle and they are neither malleable nor ductile. The elements become more metallic as we go down on a groove. That is, the non-metallic character increases as one goes from left to right in the periodic table. The non-metallic properties increase from left to right. The change from metallic to non-metallic character is not abrupt, as shown in the zigzag line of the figure. So this is a zigzag line. It is the change from metallic to non-metallic is not straightforward. It is in the zigzag line. The elements like silicon, germanium, arsenic, antimony, and tellurium bordering this line and running diagonally across the periodic table show properties that are characteristics of both metals and non-metals. These elements are called semi-metals or metalloids. Some of them are the semiconductors. Now we will take worked examples. Problem number 2. How would you justify the presence of 18 elements in the fifth period of the periodic table? Solution. When n is equal to 5, L is equal to 0, 1, 2, 3, the order in which the energy of available orbitals 4d, 5s and 5p increases. The order is 5s less than 4d less than 5p. The total number of orbitals are 9. The maximum number of electrons that can be accommodated is 18, and therefore 18 elements are there in fifth period. Problem number 3. The elements Z is equal to 117 and 120 have not been discovered. In which family or group would you place these elements and also give the electronic configuration in each case? Solution. We see from the periodic table that elements with Z is equal to 107 would belong to halogen family, that is group 17, and the electronic configuration would be Rn into 5f to the power of 14, 6d to the power of 10, 7s square and 7p5. The elements with Z is equal to 120 will be placed in group 2 alkaline earth material and will have the electronic configuration UUO, that is 8s square. Now we will answer some of the multiple choice questions. Question number 1. What is the name and symbol of element with atomic number 112? Please read the question once again. You have 4 options. Option A, copernicium Cn. Option B, oganesson. Option C, dubonium Db, symbol Db, and option D, moscovium. So you have to identify the element with atomic number 112. You have to remember the periodic table, general layout of periodic table, and mark the correct answer as copernicium Cn. Next question. An element with atomic number 117 is known as. 4 options are there: nihonium, fluorurium, tennessine, and roentgenium. Again, you have to remember the names in periodic table and mark the correct answer. The correct answer is tennessine. Meitnerium is a UPSC official name for an element with atomic number. You have to identify the atomic number for meitnerium. 4 options are given: 113, 118, 104 and 109. This also you have to answer by recalling the periodic table. You have to remember and mark the atomic number for meitnerium is 109. Next question. Anything that influences the valence electrons will affect the chemistry of elements. Which one of the following factors does not affect the valence shell? Please read the question again. Anything that influences the valence electrons will affect the chemistry of the elements. Which one of the following factor does not affect the valence shell? Option A, principal quantum number n. Option B, nuclear charge Z. Option C, nuclear mass. Option C, and option D, number of core electrons. So you have to analyze this. Let us explain. Nuclear mass does not affect the valence shell because nucleus consists of protons and neutrons. Protons, that is nuclear charge, affects the valence shell but neutrons do not. Hence, the correct answer is C. Please mark it. question. Which of the following elements shown as pairs with their atomic numbers belong to the same period? Option A, Z is equal to 19 and Z is equal to 38. Option B, Z is equal to 12 and Z is equal to 17. Option C, Z is equal to 11 and Z is equal to 21. Option D, Z is equal to 16 and Z is equal to 35. So these are pairs. You have to identify the pair with atomic numbers, with their atomic numbers belong to the same period. So we will give explanation. For Z is equal to 2, the configuration, electronic configuration is 1s square, 2s square, 2p to the power of 6 and 3s square. This is n is equal to 3. And for Z is equal to 17, 1s square, 2s square, 2p to the power of 6, 3s square and 3p square. This is n is equal to 3. That is, the period is same. So this is given in as option B. You please mark it. Next question. Match the atomic numbers of elements given in column 1 with the periods given in column 2 and mark the appropriate choice. The atomic numbers are given in column 1 and the period is given in column 2. So you have to match the atomic number with the corresponding period number. So both have been given serial numbers capital A, B, C, D and small letters 1, 2, 3 and 4 and you have to match. So options are given. The answer also has got option. That is 4 options are there. A to 1, B to 2, C to 3 and D to 4. Option 2 B is A to 2, B to 1, C to 4 and D to 3. And C, option C is A to 3, B to 4, C to 1 and D to 2. And option D is A to 3, B to 1 and C to 4 and D to 2. Here atomic number is there. First identify the lowest period. See, lowest period here is 3. So the lowest atomic number is 14. So D should match with 2. So D is matching 2 in one of the two. That is option C or option D. The next is you can match with, in one of these you have to see match highest. Highest is 56. 56 should belong to the highest period number. C should match to 4. So C should match to 4. So this is D should be correct. So you please mark it. Remember and mark it. So this is the process of elimination. First select the lowest period and lowest atomic number and match them. Next question. To which group an element with atomic number 88 belongs? Group 12, group 17, group 10 and group 2. So 88 is in group number 2 because it belongs to 88 belongs to 7th period. 7th period and it is group 2. So the correct answer is group 2, that is option D. 88 is 7s square, hence it belongs to group 2. Please mark it. Next questions. Match the column 1 with column 2 and mark the appropriate choice. Column 1 is given certain series, that is 3D transition series. lanthanoid series, actinoid series and 4D transition series. Column 2 is given Z equals 58 to Z equals 71. Z is equal to 39 to Z is equal to 48. Z is equal to 21 to Z is equal to 30 and Z is equal to 90 to Z is equal to 103. So you have to apply. So lanthanoids start from 58 to 71. That is, 4 options are given. Before that, let us write the options. A to 1, B to 2, C to 3 and D to 4. Then option B is A to 2, B to 3, C to 4 and D to 1. Option C is A to 3, B to 1, C to 4 and D to 2. And option D is A to 4, B to 3 and C to 1 and D to 2. So first is lanthanoid series starts from 58. So B to 1 should be there. So B to 1 is available only in C. So option C should be correct. Option C, that is B to 1, should be the correct answer. So option C is the, please mark it. So if you remember one, first you tally it and then you elimination process you can start. So correct answer is C. Match the atomic numbers given in column 1 with the block in which the element is placed in column 2 and mark the appropriate choices. So column 1 is atomic number 62, 47, 56 and 53. And you have to mark the column 2 shows the block number. That is block description. That is D block, P block, CF block and S block. So options are given. So options are A to 3, B to 1, C to 4 and D to 2. That is option A. Option B is A to 1, B to 2, C to 3 and D to 4. Option C is A to 2, B to 4 and C to 1 and D to 3. And option D is A to 4, B to 1, C to 2 and D to 3. So column number 1 is atomic number 62. Atomic number 62 belongs to lanthanoid, that is F block. So A to 3 should be there. A to 3 is available in option A. So A should be the correct answer. Then B should be 47. That is atomic number 47 should belong to D block, because D block starts from 21 onwards. Hence, option A should be the correct answer. Please remember and mark it. If you remember one and if you match it, then all other things you can do it. You can decide depending on by using elimination process. Atomic numbers of few elements are given below. Which of the pairs belongs to the S block? So atomic numbers of few elements are given below. These numbers are A 7 to 14, 3 to 20 and 8 to 15 and 9 17. So we have to identify the numbers which are belonging to S block. You know S block is first group and second group. So it should start with 3 and the 20 should also be in the S block. So option B is the correct answer. So you can also explain it. Z is equal to 3 is 1s square 2s to the power of 1, and Z is equal to 20 is 1s square 2s square 2p6 3s square 3p6 and 4s square. So both are ending with yes. So here option B is correct answer. Mark it. Next question. Which of the following have the same number of electrons in outermost shell? Four options are given. Elements with atomic numbers 30, 48 and 80. Option B. Elements with atomic numbers 14, 15, 16. Option C. Elements with atomic numbers 20, 30, 50. And elements with atomic numbers 10, 18 and 26. So you have to remember and follow the explanation given. So elements with atomic number 30 is argon. You have to remember it is the electronic configuration is 3d to the power of 10 and 4s square. And the next given is 48. 48 is krypton 4d to the power of 10 and 5s square. 5s square. And elements with atomic number 80 is xenon 4f to the power of 14, 5d to the power of 10 and 6s square. So the correct answer is 30, 48 and 80. Here they all belong to same number, have the same number of electrons in the outermost shell. Let us mark it. Option A is the correct answer. With this, we come to the end of our lecture on periodic table, that is lecture 2. Next class, we will take up section 3.7, that is periodic trends in properties of elements. Till then, goodbye.